All right, looking at our lesson 4 here about transformations of lines today. On the warm-up, it just says identify whether the equation represents a proportional or non-proportional relationship. Then state whether the graph of the line will increase or decrease left to right. All right, so remember, proportional relationship, we talk about direct variation, varying directly, has to go through 0, 0. The y-intercept has to be 0, which means number 1 is non-proportional. It's got a y-intercept of -9. Same thing with number 2. That is non-proportional. It's got a y-intercept of -3. But the third one, this one is proportional. It has a y-intercept of 0. And going back, it also asks us to state whether it increases or decreases. Well, number 1 has a negative slope. So that is going to be decreasing. I'm just going to draw a decreasing line. 2 would be a positive slope, so that's going to increase. And 3 is also a positive slope, so that would be increasing as well. All right, moving on to the getting started activity. Going back to when we talked about transformations previously. It said consider triangle ABC with the coordinates 2, 2, 8, 2, and 8, 8 shown on the coordinate plane. Suppose that triangle is translated in a single direction. In general, how does this affect the coordinates of the figure? So if we went 4 units up, that is in the y direction. So we'd be talking about a transformation that is x, comma, y plus 4. 4 units down would be x, comma, y minus 4. Left and right, now we're talking about the x direction. So left would be x minus 4, and then our y would stay the same. And then right would be x plus 4, and our y would stay the same. And then 2, suppose the triangle is reflected across an axis. How does that affect the coordinates? So going back to our reflection rules, reflecting across the x-axis changes the value or the sign of the y, and reflecting across the y-axis changes the sign of the x. So using our reflection rules, we can state what our new coordinates would be. Okay, continuing with that, on to number 3 on the next page. Suppose that triangle is rotated through an angle with the origin as the center of rotation. Our rotation rules from about 2 units ago, our 90-degree counterclockwise rotation rule was opposite y, x for our point. 180 was we just changed the sign of x and y, and 270 degrees counterclockwise was y opposite x. Okay, and then 4, dilating a figure. So suppose the triangle is dilated by a factor of m with the center dilation at the origin. How does this affect the coordinates of the figure? Well, we would just multiply each one of those coordinates by a factor of m. So m times x, m times y. So how might we think translations, reflections, and rotations and dilations affect lines? It's going to be just like they affect geometric figures. It will be no different. All right, on to activity 4.1. It says in this activity, we're going to investigate how the equation of a line changes as we translate the line up and down the y-axis. Consider the graph of the basic linear function, y equals x. That's the linear parent function. The line represents a proportional relationship with a rate of change or slope of 1. So it says trace the axes and the line y equals x on a sheet of patty paper. Again, doing this digitally, so I'm not going to trace it. I'll draw it onto the graph. And then keep the y-axis on the patty paper on top of the corresponding y-axis, the coordinate, and slide y equals x up and down. All right, so if we slide it up, for instance, I'll make a line, let's say where every point is moved up 3. Here would be a slide up. And if we slid it down, again, picking out some points, I'm just sliding it down 3 just to keep it the same. wants to know, how does the slope of the line change? Well, the slope didn't change. We still have parallel lines, which makes sense. We didn't dilate the line, make it steeper or less steep. We just shifted it up, down. So the slope is unchanged. How do the coordinates of the line change as you move it up or down? The x value is unchanged, and the y value changes to match the distance moved up or down. All right, 3 says translate the line y equals x 4 units up. All right, well, I did 3 on the graph, so I'm going to change that to 3 just to make it easier since I already graphed it. And it says graph and label the line with its equation. Okay, well, if we move it 3 units up, the new equation is going to be y equals x plus 3. So if we compare that equation with the equation of it translated, again, I changed that to 3. So 3 units up, what do we notice? It's the same slope. And the y-intercept moved from 0, 0 to 0, 4. Oh, sorry, 0, 3, because I moved it up 3 units. Let me change that. 0, 3. Okay, now we did the opposite. Again, I already drew the line down 3 units, so I'm going to change that to a 3. So we graphed the line. Now, if we write that equation, it would be y equals x minus 3 because it moved down 3 units. So how did that graph change? Again, same slope. But now the y-intercept moved down from 0, 0 to 0, negative 3. So for any x value, how does the y value change when you translate it up or down? The y value increases or decreases by the magnitude of translation. So if it was y equals x plus 10, that means it had moved up 10 units. So are the new translated lines proportional or non-proportional? They are non-proportional because they do not go through 0, 0. Got to go through 0, 0 to be a proportional relationship. All right, on number 7, the lines on the graph are translation of the line represented by y equals x. So A, describe each translation in terms of translation up or down, and then write the equation. So for line A, I'm going to label them out here. That line has been translated 6 units up. We see a y-intercept of 6. So we have y equals x plus 6. For line B, it's translated up 2 units. Got a y-intercept of 2. So y equals x plus 2. For line C, it's got a y-intercept of negative 5. So y equals x minus 5. And then D, it's got a y-intercept of negative 7. So y equals x minus 7. So the first 2 shifted up, second 2 shifted down. The slope of each line is all the same. So slopes are all 1 because the coefficient of x is 1. We're going up 1, right 1 on those graphs. Okay, so it says the lines drawn on the coordinate plane in question 7 represent parallel lines. Remember that parallel lines are lines that lie in the same plane and do not intersect no matter how far they extend. Parallel lines are always equidistant from each other. So 8 wants us to analyze the graph of each line and its corresponding equation. How can you verify the lines are equidistant? You can show that for any given x value, just say any x value, the difference in y values would be the same. So would be equal. They'll always be the same distance apart. Okay, and how can you tell by looking at a set of equations that the lines are all the same? All would have the same slope. Remember, that's the coefficient of your x. So based on our investigation, we're going to complete this sentence. The line y equals x plus b is a vertical, I'm just going to put vert translation of the line y equals x that maps the point 0, 0 onto the point 0b, whatever that b value is. It maps the point 1, 1 onto the point 1, 1 plus b, adding whatever that b value is to it. And the next page, we're going to look at dilating linear equations. So again, the graph of the basic linear equation y equals x is shown. We're going to investigate how that line changes when the rate of change or slope changes. So again, we're not going to use a piece of pasta, as it says, since I'm doing this digitally. I'll draw some lines in there where necessary. But the main thing is we're going to get our output values for given x values based on these dilation factors. So the first one is our parent function. The output values for the x's of -2, 0, 1, 2, and 4 would be -2, 0, 1, 2, and 4. And then if we're multiplying those x values by 2, dilation factor of 2, we'd have -4, 0, 2, 4, and 8. By 1/2, we'd have -1, 0, 1/2, 1, and 2. And then by m, it would just be -2 times m, 0 times m, 1 times m, 2 times m, and 4 times m. So just graphing a few of these equations. Again, first one's already shown. I'm put this one in blue. 2x would be a slope of 2, going up 2, right 1. So we can see that line got steeper as it was dilated by a number bigger than 1. And for comparison, the one that's 1/2, I'll do in red, that's a slope of 1/2, so up 1, right 2. And we're going to see that that line got a little bit flatter, shallower, you might say. So a slope of less than 1, between 0 and 1, means that we have a flatter line. Okay, it says based on our investigation, we're going to complete that sentence about dilations. So the line y equals mx is a dilation of a line y equals x that maps the point 0, 0 still to the point 0, 0. So we're staying at the y-intercept. It's not shifting up or down. And maps the point 1, 1 to 1, 1 times m, multiplying by that dilation factor. So still looking at that dilation, it says consider y equals 3/4 x. Use transformations to complete the table of values. So again, first column there is our parent function. Those values -2, -1, 0, 1, and 2. And then 3/4, we'd have -3/2, -3/4, 0, 3/4, 3/2. Okay, so we can see if we were to graph those, we would see that we had a line that was flatter, again, since 3/4 is less than 1, and it's going to produce a flatter line than the parent function is. All right, now number 4, we're going to look at reflecting it. It says the equation y equals -x is a transformation of the parent function y equals x. How are the equations similar? How are they different? Okay, so y equals x, our parent function is going to look like this, increasing with a slope of 1 going through 0, 0. Y equals -x is going to be reflected and turns into a decreasing graph with a slope of -1. So how are they similar and how are they different? You could say they're similar that the absolute value of the slope are both 1, but 1 is reflected, producing a decreasing graph. So it is going down from left to right. So we graphed both the equations already. So if we want to make a statement based on that, based on an investigation, completing this sentence, y equals negative x is a reflection of the line y equals x that maps the point 0, 0 to still on 0, 0. We're not shifting up or down. It maps the point 1, 1 onto 1, negative 1. It flips it and reflects it across that x-axis. All right, activity 4.3, using transformations to graph these lines now. So we got dilations and shifts up or down. So it says we've explored how the basic linear equation y equals x is translated to create equation y equals x plus b, or dilated to create the equation y equals mx. So we're going to combine these and graph these lines. So that first line, I'm going to do in black here. Y-intercept is still at 0, and we got a slope of 2, up 2, right 1. So there would be that line. Second one, I'm going to do in red. This one has a y-intercept of 3, it's up 3, and then a slope of still 2, so right 2, or up 2, right 1, I should say. So here is that line. Third one, I will graph in green. Y-intercept of negative 5, slope of 2, so up 2, right 1. Oh, all my graphs move. There we go. And we get this line. I could draw it straighter, it'd be a little better. And then the fourth one, y-intercept of 5, still slope of 2, up 2, right 1. So pretty close to that red line, but it's still the same slope, you'll notice. So we got a bunch of parallel lines here. So what do all the equations have in common? They all have the same slope. Same slope of m equals 2. Okay, and using transformations, we graphed each equation, describe the relationship among all the lines. Well, because they have the same slope, they are all parallel. Parallel lines create the same slope. Okay, we're going to see something similar on the next one. Bunch of more equations. You'll notice they all have the same slope again. Might be a good idea time to try to pause it and graph yourself and then unpause it to check your work. So this first one, a y-intercept of 0 again, slope of negative 3. So we're going down 3, right 1. Second line, a y-intercept of negative 2, down 3, right 1. 1, 2, 3, pretty close to that other one, but we're a little different. It's going to be very close. For the next one, I'm going to do in blue, y-intercept of positive 5, slope of negative 3. So again, down 3, right 1. And then the last one there, I'm graphing yellow, y-intercept of negative 8 with a slope of negative 3, down 3, right 1. So we get one more parallel line there. Straight as I can draw them. So again, what do they all have in common? They all have, again, the same slope. In this case, the slope is negative 3. Okay, we use transformations to graph each equation already. C, describe the relationship among the lines. Again, they are all parallel because they have the same slope. And it says describe and use strategy to verify the relationship among the lines. And you could just verify they're parallel by the vertical distance between x coordinates are all equal. So in other words, the x-coordinates of each one of those lines, if we look to the line next to it, it would be equal distance for each x-coordinate along the two lines you're trying to compare. All right, now we're going to look at one without having the graphs. Let's consider these equations without graphing, describe their graphical relationship again. Well, you'll notice again, they all have the same slope, so we all have parallel lines again. So to explain how we determine the relationship, they all have the same slope of m equals 1/2. The only thing different is their y-intercepts, the shifts up or down they have made. So for 4, determine the quadrilateral form by the joining points 3, 1, 8, 1, 10, 5, and 5, 5 is a parallelogram. So let's graph those points. We got 3, 1. Nope, not there. Let's try again. 3, 1 is here. That's our A. And then we got 8, 1. That's our B. 10, 5. C, and then 5, 5 is our D. So it looks like we do have a parallelogram. And how can we tell that? It's the slopes of those sidelines. These slopes are equal. So we could say, yes, it is a parallelogram, and the slopes of sides 1 and 2 are equal to 2. All right, so now that you understand linear equations in terms of transformations, you can use transformations to graph the lines. So we're going to graph y equals 3x minus 4 using transformations of the basic linear function y equals x. So we can see either the dotted line is our parent function y equals x, and we've graphed the line 3x minus 4 using two transformations. First, we dilated it by a factor of 3 to change the slope to 3 over 1. So the slope changed from up 3 to right 1, 3 over 1. And then a vertical shift of down 4, move that y-intercept down to 4 on the y-axis. And we end up with our new line that I'll star right here of y equals 3x minus 4. Okay, so the next couple of pages is just going to practice graphing a few lines now that we know all our transformations. So for letter A here on 5, we have a shift up to 5, vertical shift, so y-intercept of 5, and a slope of 1/2. So right up 1, right 2. And there's our line. For B, we got a shift down to negative 3 and a slope of 3 over 2. So up 1, 2, 3, right 2. 1, 2, 3, right 2. And we get this line. So 3 over 2 is it's bigger than 1, 1.5. So we get a line that's a little bit steeper. All right, so last thing we're going to look at in this lesson, activity 4.4, is reflecting and rotating parallel lines. Excuse me. Okay, you've learned what happens when a line or a figure is reflected across the y-axis. What happens if we reflect a pair if you reflect a pair of lines across the y-axis? Excuse me. So line AB, line segment AB, and line segment CD are shown on the coordinate plane. So what is the relationship between those two lines? Well, they are parallel, and we can tell that's because they have the same slope, so they're parallel lines. So trace line segment AB and CD onto patty paper. Again, just doing this digitally, so I'll reflect it without the patty paper. If we were going to reflect those across the y-axis, point C is 3 units from the origin, so I'm going to go 3 units from the origin the other way. Point D is 8, and then down 1, so 8, down 1, and then point A again, 3 units from the origin, and then point B, 8 and up 1. So we get the two lines that look like this when we're reflected across the y-axis. So the coordinates of the new AB and CD. A is at negative 3, 2. B is at negative 8, 1. C is at negative 3, 0. And the new D value, new D point is at negative 8, negative 1. So the relationship among the new segment AB and the new segment CD is still parallel lines. That did not change the fact that those lines are parallel just because we reflected them. So it says extend segments AB, CD, and the new AB, CD to create lines AB, CD, and the new AB, CD. So in other words, if we were to make those continue, talking about lines that look like this and lines that look like this, going the other direction. Oop, that's not a very good one there. Let me try that again. Close as I can. So if we continue those lines, what do we notice about the relationship? They're going to remain parallel no matter how far we extend them. So they remain parallel when extended. Okay, and then reflecting parallel lines across the same line of reflection results in lines that are still parallel. Again, if they're parallel and we reflect them, they are going to remain parallel. All right, now it says let's explore what happens when the segments and lines created from those original points again are rotated instead of reflected. So they gave us the line segments. We're going to rotate each point 90 degrees. So remember our 90-degree rule is negative yx. So our original points here, A is at 3, 2. B is at 8, 1. C is at 3, 0. And D is at 8, negative 1. So if we reflect those based on that rule, our new A value is going to be at negative 2, 3. Our new B value is going to be at negative 1, 8. Our new C value is going to be at 0, 3. And our new D value is going to be at 1, 8. So if we graph those points, negative 2, 3 would be here. Negative 1, 8 would be up here. 0, 3 would be there. And 1, 8 would be here. So there's our lines rotated 90 degrees. So there's our new coordinates listed out to answer question A. All right, so let's look at what that relationship. What is the relationship between the line segment, the new AB and CD? Again, they are still parallel. That is not changing. Okay, if we rotated the original point 180 degrees to create a new set of points. Okay, our 180-degree rule is negative x, negative y. That would result in the new A being negative 3, negative 2. The new B being negative 8, negative 1. The new C, let's see, I wrote down C. C was 3, 0, so negative 3, 0. And the new D would be at negative 8, 1. So there would be our new points rotated 180 degrees. If we were to graph those, they are still going to be parallel. I will go graph those just so we can see the difference in those. So those points were negative 3, negative 2, negative 8, negative 1, negative 3, 0, and negative 8, 1. So there we see those two lines. And again, it created parallel lines, even though they rotated 180 degrees. Okay, again, if we extend those line segments, any of those line segments we created, what are we going to notice about them? Well, each pair of line segments is still parallel. So each pair, let's see if I can get that back. If I can't, if you did miss that, just rewind it so you can fill that in. Accidentally erased. So each pair of line segments is still parallel. So rotating parallel lines results in lines that are still parallel. That does not change parallel lines. They're going to remain parallel even when rotated. All right, so last, finishing up here on the page, let's talk the talk. Which transformations of linear graphs result in parallel lines? So A, dilation. No, dilations, that's going to make it steeper or flatter. So that does not result in a parallel line. Translations up or down? Yes, because we're not affecting the slope. A reflection across the x-axis. So when we reflect it, no. It is not going to create a parallel line. They will intersect at that point. And then rotating 90 degrees, again, if I went back to this page, 90 degrees was the black to the blue lines. That is still, a rotation 90 degrees is going to create lines that intersect. So if I just take one of them, I don't want you to confuse thinking about the pair. If I rotated this 90 degrees, they're going to intersect now. They're no longer going to be parallel. So no, it creates intersecting lines. All right, and then on your own, you can come up with some graphs for question 2. A lot of ability of yours to come up with your own. It's not necessarily a right or wrong answer. As long as it fits the criteria, you are good. So it says create and graph 4 linear equations that represents lines with the same slope and label each line with its corresponding equation. So you just want to come up with 4 linear equations, same slope, and 4 different y-intercepts so that you have 4 parallel lines.